everyone, and thanks for joining us today for this new series of webinars on how electron diffraction is transforming research across the fields of materials, life sciences, and chemistry. My name is Fraser White, and I'll be your host today. I'm joined by today's presenter, Dr. Pierre Lamagares, who's our Director of Scientific Support, based in our American offices at the Woodlands near Houston, Texas. Pierre has a lot of experience running samples, both of small molecules and proteins with X-rays, and of course, more recently, with electrons. Over the next 6 months, through a mixture of presentations from our own staff and prominent researchers, we'll introduce the technique and how it's opening new doors for researchers. So if you're a structural researcher using single crystal or powder techniques, or you have a need to gain structural insights into compounds which are difficult to crystallize or available only in low quantities, then please do stick around, as we're sure there'll be something interesting for you in this series. So before we get to the main presentation, I just wanted to inform you of a few quick items. If you'd like to ask a question, please do so using the Q&A button. These questions will be read out at the end and as time allows. Any unanswered questions that we have left over will be responded to after the session. Where applicable, please try to include the slide number so that we can more easily understand the context. The chat is open, but please note that if you ask questions there, we might miss them, as we will not be expecting them there, and they may get lost up in the history as new messages appear. We will also be recording this webinar. The recording will be available from tomorrow. If you have any trouble watching the presentation live, then we recommend catching up via the recording, as it's unlikely we'll be able to resolve some of the technical problems you might have during the live webinar. Okay, and with that said, I'm sure you're all eager to hear what Pierre has to say, so thank you for your patience during the introduction, and I will now yield the floor to Pierre. So Pierre, please take it away.
Okay, thank you, Fraser, and welcome everyone to our webinar series about MicroED. So as Fraser said, this is the first episode, so there will be one episode per month for the next few months. And each episode is going to be dedicated to discussing how electron diffraction is indeed reshaping materials, life science, and chemistry research. The presentation will be given by scientists from Rigaku, as well as from other research institutions. And for my part, I am one of the crystallographers at Rigaku. And so in this first episode, I will talk about crystal structures in general first, and then move on to getting or to discussing how crystal structures can also be obtained from electron diffraction. The thing is that indeed electron diffraction has been gaining a lot of interest in the past few years, and that's because it has become an analytical tool available for home laboratories. And so in this first, so the agenda will be as follows. In the first part, I will remind everybody what crystal structures are and the critical information they provide about the structure of the molecules and their crystal form. So that may be known information for some of you, but we may also have today in our attendance people who are not too familiar with crystallography and crystal structures. So that's why I'll have this first part, or I'll start with this first part. The second part will be devoted to explaining how the characteristics of electron diffractions are used to analyze difficult samples. And lastly, I will briefly introduce each of the episodes that will follow this presentation in the course of the next few months. So I said a minute ago that indeed electron diffraction had become an analytical tool available in the home lab. And I thought that that was a good time rather, to ask you guys our first polling question.
Yeah, so you've probably seen the poll. Actually, already we have 80 people have answered. I'll just give it a minute or so for people to continue to answer. But the question is, did you know that electron diffraction is now a tool available in the home lab?
It looks like we have a split 1/4, 3/4, and 3/4 of the attendees actually do know about electron diffraction, which is quite encouraging.
Okay, so I'll end the poll there and publish the result.
Yeah, indeed. And so 26% of the people not being familiar yet with electron diffraction. Thus the point of this series about MicroED. But it is indeed encouraging that 3/4 of the people knows about electron diffraction.
Absolutely.
So let me get going then, and then so move on to the first part of my presentation. So again, this first part, in this first part, I will go over what a crystal structure is and how the information that can be derived from it helps your research. At the end of the day, that's what you want to know, right? So let me start by asking a few painful questions. So how often do you find yourself struggling to unambiguously characterize a compound? And here, I'm not talking about characterizing the properties of the compound. I'm talking about structurally characterizing the compound, what the molecule looks like, and so on and so forth. Second question is, how often do you find yourself wondering whether in your sample you only have one species, one phase, or one polymorph, or you have several phases or polymorphs coexisting? Lastly, how often do you find yourself wishing you could use the solid state structure of your compound to try and explain some of its physical properties? Now, you may use different analytical methods such as NMR, FTIR, solid state powder, but those methods don't have all the answers. For instance, you can't get the absolute confirmation of a molecule from an NMR spectrum. And another important point is that other or many other analytical methods deal with a bulk material, right? You measure on everything you've got in your material, including impurities, side products of your synthesis, polymorphs, and so on and so forth. So you measure on everything, and it might become really hard to interpret the measurements that you get from it. And really not being able to answer the questions shown on the screen right now, so may prevent you from publishing altogether, or at least force you to publish in a smaller scientific journal. But also it may slow down your project, or maybe even halt the project altogether because, well, you don't know really or you're not sure what your compound is. So how to get answers to these questions? Well, you can get all the answers from the crystal structure of your compound. And this is really because the crystal structure is the only method that gives you a clear picture of the molecules of your compound in a pure crystal form. So there are three concepts here, really. Therefore, three colors in my sentence. So there's the concept of the picture of the molecule, the crystal form, and then the fact that the crystal form is pure. So let's investigate a little bit more what these 3 points or 3 concepts are. So first, the picture of a molecule is when each and every atom of that molecule can be located and identified. So on this picture here, you see this is the structure of a molecule of acetaminophen, also known as paracetamol. So those gray ellipsoids here represents carbon atoms. The white ones are hydrogens. The red ellipsoids represent oxygen atoms, and the sole blue ellipsoid here represents an atom of nitrogen. So once you can place each and identify each of the atom or the atoms, so you can see how they link with each other, and therefore you can actually see unambiguously the picture of your molecule. And we call that also molecular connectivity. So now let's talk about the crystal form. So the crystal's form is how molecules arrange with each other in a periodic way to form a crystal, so therefore in the solid state. So this picture here represents a view of the crystal structure of this specific polymorph of acetaminophen, or again, a paracetamol. And when you go along the vertical axis as well as the horizontal axis, you see that the molecules repeat each other in a periodic way. That's the definition of a crystal. And here is another view of the same molecules arrangement, just seen from a different direction. So the way, again, or the crystal's form is the way molecules pack up in the crystal, and this is also called crystal packing. And now, why do we say that the crystal form is pure? So here is pictures of really nice-looking crystals. So a crystal represents a single arrangement of molecules, a specific arrangement of molecules. So in each one of these crystals here that you see on the picture, you may have, or each one of these crystals may be made of molecules from a single compound, or can be the combination of molecules from different compounds, including water molecules. It doesn't matter. And each one of these molecules can also represent a specific or a different arrangement of molecules, okay? But each crystal that you see on this picture has to represent a specific arrangement of molecules. So a crystal is always specific to a phase or a polymorph. So as a result, when you measure single crystal diffraction from a single crystal, you always measure on a pure form or pure polymorph. So now let's see what applications can be derived in your scientific research from getting the crystal structure. Let's talk about first molecular connectivity. So the first thing might be quite obvious now, but this is an unambiguous identification of your compound. Again, you place each and every atom. So here is a picture of a molecule that we got, or the crystal structure of that compound we got via electron diffraction, and by collaborating, with one of our users here. And we were co-authors in that paper in Science last year. So this crystal structure was obtained with electron diffraction. And again, each and every atom was defined or located and placed by the electron diffraction study. This is a crystal structure and an identification of the compound that could not be obtained otherwise using X-ray crystallography and or other analytical method. Finally, these people could characterize that compound after we solved the crystal structure. A crystal structure will also yield the absolute configuration of a molecule. So here is a picture of the amino acid tyrosine. The carbon atom pointed out here by or shown by the green arrow represents or is a chiral center. So the four chemical groups linked to that carbon atom are different. So therefore, this is a chiral center. And once you can, again, locate and identify each of the chemical groups linked to that chiral center, then you can define or determine the handedness of that compound. And again, that can only be obtained with a crystal structure. Third, you can also distinguish between a salt and a co-crystal. Here is a study that we did a couple of years ago where the same two molecules, the same two molecules crystallized as a co-crystal, and that's the top picture, where each of the molecules were in their neutral state. So this is what we call a co-crystal. However, the same two molecules could also crystallize as a salt. You see here that this hydrogen atom that I'm circling with my cursor is now linked to the nitrogen instead of being linked to the oxygen like on the top picture. So as a result, the left-hand side molecule now bears a plus charge, whereas the right-hand side molecule bears a minus charge. We have a co-crystallization of a cation with an anion, and therefore this is a salt. And sure enough, these two crystal structures had a different arrangement in the crystal. Okay, and that could only be obtained also via getting the crystal structure. The last thing I'm going to say here about molecular connectivity is that you can also determine as to whether you have guest molecules within the pores of a host molecule. So, of course, everybody is thinking of metal organic frame compound, but here I'm showing the crystal structure of a protein catalase. More precisely, that picture shows the active side inside the protein catalase, and in that active site here, there's a heme ligand. Then connecting to that heme ligand, there is a amino acid of tyrosine, and you see here that the red atom at the tip of the tyrosine molecule connects here with the iron atom within the heme ligand. And so this is via this crystal structure that this could be determined. And this is single crystal diffraction or crystal structure are often used by structural biologists to determine as to whether drug candidates have been inserted in the active site of a protein molecule. And so this fits into the category of determining as to whether a guest molecule has been inserted into a host molecule. And a little bit later, I will talk about metal or organic framework in a little bit more details. So let's move on now to what you can get from having the crystal packing of your compound. So first, you can determine as to whether you have a hydrate or a solvate. There is an example of a crystal structure that we determine via electron diffraction. Again, where two molecules, here is one, and here is the other one, co-crystallize by including water molecules in the crystal lattice. And only once the crystal structure was determined, could we also realize that water molecules were included into the crystal. And the last thing or the other thing that crystal packing can also tell you is which polymorph or polymorphs you may have. So let me use basically the same example as on the previous slide. It's just that on the previous slide, I only showed the right-hand side co-crystal, including water. It turns out that the same two molecules, if you look closely, you can see that these are the same two molecules on the left and on the right. So those same two molecules can also crystallize, but this time without including water molecule in their lattice. And there you have two different polymorphs, which was again given a result that was given by the crystal structure. So there you have it. All those critical information stemming from crystal structures. And again, this is unambiguous information as you see all the atoms in your crystals. So this is what I wanted to say about crystal structures in general. And maybe I can actually make a first stop here, Fraser, and answer a few questions, if by any chance there are any already.
We don't have any questions from the audience right now, but I can ask one to give some people a chance. Okay, so here's a question just come in actually. So if a synthesis yields an unexpected product, or the starting materials did not react with each other, will I get crystals of those unexpected compounds?
Yeah. So yeah, indeed. So your synthesis didn't go the way you expected, and you have different species in your compound, including unreacted starting materials, or even a side product, and so on and so forth. So yes, the answer is you will. You may be able, or you will have crystals for those compounds, provided that those compounds can crystallize in the solution that you have at that moment. Some compounds just can't crystallize; they are too soluble in that very solvent that you have at the moment, and therefore will remain in solution. So you always have that possibility. But if the conditions, the solvent conditions are proper for a compound to crystallize, then even if they are side products of your synthesis or unreacted material, they will yield crystals. And once you mount one of those crystals on what is called a diffractometer, you will get the crystal structures of those unreacted compounds or side products. But again, it only depends on as to whether those compounds can crystallize in the solvent that you are using at that moment.
Just had a few coming at once. Okay, so the next question, I've had some examples where another method would suggest a certain molecular structure, but the crystal structure would show a slightly different molecule. Which should I believe?
Yeah. So at the end of the day, the crystal structure, and that was the point of the first part of my presentation here, the crystal structure is the ultimate answer. Again, this is a clear picture of your molecule, right? So, however, like I said, an NMR spectrum, for instance, will give you the trace of all the compounds you have in solution. And therefore, you might have derived a different conclusion from the NMR spectrum than the one that you get from the crystal structure. So that's always a possibility. The other possibility is that so you weren't too sure as to whether what oxidation state, for instance, a molecule or a coordination compound had. You thought it was iron 1, for instance, and so it turns out that in the crystal structure, it is iron 2, and it is iron 2, for instance, because maybe the counter anion, for the counter anions, there are 2 perchlorate anions. So if you have 2 perchlorate anions, then these 2 bear a charge of -2. Therefore, your compound must bear a charge of +2 to ensure electron neutrality. And once you get that from the crystal structure, that's it. There is no doubt possible. Your iron compound is +2, even though you might have thought that it was +1. Another example is as to whether sometimes you have a hydrogen atom bound to a nitrogen atom or not. You thought there wasn't any, and the nitrogen was in its neutral status, but the crystal structure shows you that there is clearly a hydrogen atom bound to that nitrogen, and now the nitrogen bears a plus charge. Again, if the crystal structure shows you so, then it's got to be correct. Okay? And then in the crystal structure, there are a few parameters that you can look at to check that everything is correct. This is, of course, the R factors, the reliability factors, which are R1 and R2. You can also check the remaining electron density in the data to make sure that you haven't forgotten to assign any atoms. So there are things to check in the crystal structure, right? But once all these parameters check out, then the ultimate answer is the crystal structure.
Okay, we have 3 more questions in the Q&A, but I suggest that we save those to the end at this point and carry on with the presentation just to make sure we get to the end in time.
Okay, cool. Yep, thank you. All right, let me now talk about the beautiful tool that we have to determine crystal structures, and that tool is called crystallography. So I'm going to describe first how X-ray crystallography works, because this is the most known type of crystallography. So for X-ray crystallography, you take an X-ray beam from a source, and that X-ray beam goes through a collimator and is monochromatized and focused onto a crystal. The crystal itself is mounted on what is called a goniometer head. So going through the crystal, the incident beam is diffracted in a number of discrete reflections. Of course, those reflections come out of the crystal in all directions of space, but we can collect only so many of them at once. So we put a 2D detector behind the crystal, and we record both the location of those reflections and their intensity on that detector. We include or insert those data into fancy calculations, which are called Fourier transforms, to get a so-called electron density map. And the electron density maxima in that map, as shown here on that by my cursor, basically determine where the atoms are located, and therefore yields a model for your compound, and we call that a molecular model. Okay, and so this is where manufacturers like Rigaku come into the picture, because we build diffractometers that will allow you to do exactly what you see on the screen. So we build the hardware and software to control diffractometer and solve the structure, and you do basically the crystal. Okay, so those crystals here is an example. So those crystals usually for X-ray crystallography have to have dimensions of at least 1 micron, but they can be of a few hundreds of microns as well. Okay? So if you want to learn more about crystallography, I would strongly suggest that you read this book here entitled Crystallography Made Crystal Clear. This is a really nice book written for beginners. Okay? So then, I said that we do the hardware and the software. Manufacturers like Rigaku do the hardware and software, and you are on the hook basically to still make the crystal. So, however, as soon as you can make a good enough crystal, and I'm emphasizing here good enough, it doesn't have to be a super crystal like you you may get from a standard, one of those standards used for X-ray crystallography. Right? Just a decent crystal, good enough crystal. This is how a typical X-ray diffraction experiment should look like. So on the left-hand side of your screen, this is an image of the detector, and you see that the reflections, those white dots, are recorded on the face of the detector, both their location and their intensity. On the right-hand side, the program then starts reducing the data, basically integrating the intensity of those reflections. And then once the data reduction is complete, the program will then try to solve the crystal structure of your compound. And hopefully you get actually a good model for your compound. Now, it doesn't have to be a complete model every time, but at least a pretty good model or starting model that you can then quickly finish up manually. So that's how you will be surprised as to how often it works that way from the moment that you can grow a decent crystal. However, of course, nature being nature, all crystals don't behave that well, and then the crystal quality will sometimes be much poorer and even too poor to get good data. So crystal quality, really how well a crystal diffracts, is mostly influenced by two criteria: the tightness of the crystal packing or the packing of molecules in the crystal, and also the size of the crystal. Okay? So here is, again, the picture of the crystal structure for that specific polymorph of acetaminophen. And you see how tight the molecules are arranging with each other in the crystal form. And really, it's not hard to understand as to how such a small and flat molecule can really get a tight packing in the crystal form. However, this is not always the case, and then the size and shape of the molecule you're trying to crystallize will greatly influence how tightly they pack in the crystal. So the bulkier the molecule, or even the longer the molecule, meaning the more flexible the molecule is in solution, and the less tight the crystal packing will be, thus decreasing crystal quality. Presence of solvent or not may also alter crystal packing, as well as voids left in between molecules in the crystal form. The more voids you've got and the larger the voids, then the weaker the crystal and the poorer its quality when you put it in an X-ray beam. But the second criterion here influencing crystal quality or diffraction quality is really the size of the crystal. So here I've got a picture of a small crystal. If you see it here, that little dark piece of crystal at the tip of the loop. So the length of it was decent, 45 microns, but you see that the cross section was only 13 microns by 13 microns. So that's a really small crystal. And there are some compounds that basically won't crystallize in large dimensions. And sometimes you're actually stuck with a precipitate. You know, you can't get beyond a precipitate. Even a small crystal like the one shown on the screen can't be obtained, whatever solvent mixtures you use, and so on and so forth. Okay, so these will alter crystal quality, and the ultimate consequence is that you also lost diffraction intensity. And suddenly the data is too weak. You don't have enough data or enough strong data to solve the crystal structure of your compound. Okay. However, this is again where manufacturers like Riga come into play, where we build diffractometers which generate X-ray beams of various strength. So moving from left to right here, you are moving through stronger and stronger X-ray beams, all the way even to synchrotron beam lines. So synchrotron beam or X-ray beams generated at synchrotron beam lines are the most intense in the world, for sure. Okay. So again, moving from left to right using stronger and stronger X-ray beams, so scientists can afford to use smaller and smaller crystals. And that's what you see at the bottom of your screen here, all the way down to crystals that are about a macron in dimensions. So that's, in a nutshell, that's what or how X-ray or single crystal diffraction experiments work, and how they are, or the type of instruments that are used, meaning X-ray diffractometers, to actually use that technique. I thought it would be good to make a second stop here and ask the audience our second polling question, Fraser.
Yep, so I've just launched the poll for you. So the question this time is, how often do you use single crystal diffraction to characterize your compounds? So we'll just give this a minute or two to run through. So far, it's looking like most people are using single crystal diffraction. Okay. So yeah, it's looking like over half are using it either often or occasionally, and only 20% never use it.
Okay, yeah. So that makes about half of the attendants never using or only occasionally using single crystal X-ray diffraction, and 20% of them really are never using it. So again, this justifies this. I mean, my explaining to you guys how to get crystal structures and how single crystal diffraction actually works. So getting back to my presentation then now, let's try to move on a little bit further and basically convince our audience here, or more of our audience, to actually use diffraction, single crystal diffraction, to characterize their compound. So I said that X-ray diffraction works on many samples up until or as long as you can grow crystals which are at least with dimensions of about 1 micron. However, turns out that at about 1 micron, you hit a wall if you're using X-ray diffraction. So X-ray crystallography cannot handle really samples that have dimensions below 1 micron. This is when you need to turn to electron diffraction. Electron diffraction can actually analyze submicron particles, just like the one shown at the bottom right of your screen. Okay? And that leads me to my second part, how electron diffraction can save the day. So on this picture, on this slide here, I have an X-ray beam on the left-hand side and an electron beam on the right-hand side. On the left-hand side, you see that X-ray photons are being diffracted by the electron density around the nucleus of atoms. Whereas on the right-hand side, an electron beam is diffracted by the Coulombic potential around the nucleus of these atoms. And as a result of that, the interactions of an electron beam with crystalline matter is much stronger than the interactions of X-ray photons with crystalline matter. And it can be stronger by 4, 5, or even 6 orders of magnitude, depending on your crystal, the size, and so on and so forth. So this is a huge gain in interactions when you move from an X-ray beam to an electron beam. And as a result, electron diffraction has 2 very important features: the crystal size that you can analyze and the sample amount that you need to actually go ahead with an electron diffraction analysis. So like I just said, crystal size, you can analyze now submicron crystals. But think about what that means. That means that you can do single crystal crystallography on a crystalline powder. Even when you're stuck with a precipitate, you can't crystallize your compound. If your powder or your precipitate is crystalline or crystalline enough, you should be able to get the crystal structure, or at least to measure diffraction data using an electron beam. And then, because you need really one or a handful of these tiny particles, as shown here on the left-hand side, you really need minute amount of powder. And really here, the amount of powder that you need, this is not even for the electron beam. It's not even to run your electron diffraction analysis. This is for your eyes to see the sample when you prepare it. So here are a few examples of powder on glass slides for 3 different compounds. So tyrosine on the left-hand side, an organic co-crystal in the middle, and a metal organic framework, the well-known ZIF-8 MOF here, based on nickel on the right-hand side. So typically, you would take a transmission electron microscope grid, like the one shown at the bottom right of your screen, and swipe it through your powder sample, so that now you have a multitude of powder grains on the face of your grid. that grid size is 3 millimeters in diameter. So if I take the example of tyrosine, this is a submicron particle that we use to collect electron diffraction data. So if that circle represents a diameter of 2 microns, so that means that this at sample position, so that means that this particle was even a bit less than half a micron in size. The thickness of that particle, we don't see it because it lies flat on the grid. But usually, to work with electron diffraction, the thickness of your grains or of your crystallites must not be more than 200 to 300 nanometers. Here is a diffraction image that we got from that particle. Now, as I mentioned here at the bottom of the screen, this is only one image from a series of rotational images that we got throughout the data collection. Indeed, so the grid and therefore the crystal is rotated in the electron beam. So you get many diffraction images throughout the rotation range, and this is just one of those many images. And here is the crystal structure that we got from that submicron particle. So this was the example for tyrosine. Here is how we a particle of that organic crystal that we used to collect data. See at the top here again a sub half micron particle and a nice diffraction pattern we got out of it. For the ZIF8 MOF compound, again, we used a particle that was not even as large as a half a micron, and you see at the bottom there underneath the nice diffraction pattern that we could get from that one particle. And I've got a fourth example here. I don't have a picture of the powder sample for that compound, which was a zirconium coordination complex. But I still put that example on that slide because you see at the top right, that tiny needle is just beautiful. So the thickness of that needle is maybe 40, 50 nanometers only. And you see still the nice diffraction pattern that we got from it. So again, these are two big advantages of using electron diffraction, and I would suggest that you read the review that several of my colleagues at Rigaku wrote about electron diffraction a couple of years ago. So this is really a scientific review that we wrote here at Rigaku. The last thing I'm going to say about electron diffraction is that because you have a multitude of crystals at once on the surface of the grid, of the TEM grid, you can run high throughput screening of polymorphs on powder samples. Okay, and again, this is because you have a lot of the tiny grains on your grid, and so when you look at at the face of your grid with the electron microscope, once the grid is loaded into the electron microscope, then you see all these particles that you would like to analyze. So then you use the software to put them all in a queue, and ask the software to get back to each one of these particles one by one, without any user intervention in between, center the crystallite, and then collect data on it. And here is an example of how that should look like. The program auto-centers the particle into the center of the beam and collect a certain range of rotational images. Then moves on to the next crystallite, auto-centers it, and collect a data set on that second crystallite, and so on and so forth. And of course, behind the scene, the data reduction is also happening automatically without any user intervention. So hopefully when you come back the next morning or a couple of hours later, when you go back to your machine, you have a whole bunch of data sets collected, processed, and maybe even a few crystal structures solved. So that's bulk or high throughput screening of polymorphs that you can do with electron diffraction. And I'm going to make another stop here so that we can ask the audience our third and last polling question.
Okay, so I've already launched the poll. The question is, how often do you use electron diffraction to characterize your compounds? So I think this one will probably go the other way, and most people
indeed.
Never. We can see it coming in now. It's more than I thought are using it. About 40% have never used it.
So 40% have never used it, and 5% did not know of this technique. So which is exactly, again, why we are running this series on MicroED, because this is really not a technique that people that everybody knows about, or at least that people don't know it is available in the home lab at the moment. Okay, so now let me move on to the last part of my talk. I just need a few minutes to go through that. I will now here describe what you will learn in the upcoming presentations in this webinar series for the next 5 to 6 months. So the first presentation will be given to us by Dr. Robert Bucher. So Robert is the global manager or global product manager for our own electron diffractometer that you see here on the left-hand side of the slide, the Synergy ED. So once Robert will have explained how an electron diffractometer works, so he will present several real-life examples of electron diffraction projects we carried out in Rigaku labs across the world. So indeed, we at Rigaku have collaborated with many academic labs and private companies for the past 3 to 4 years, and we probably have solved several hundreds of crystal structures by now. So obviously, we've got a lot of stories to tell, and Robert will take us through some of these stories. Okay? And then he will also tell us about the bright future that we think electron diffraction has in front of itself. And we see the gain in interest in electron diffraction so far as going exponentially. And we think it's going to keep going, and that we are only at the bottom of that exponential curve. So to excite your appetite a little bit about what's coming up in Robert's presentation, let me give you a few examples here. Here is an example where the uncertainty about the nature of which polymorph existed for this compound containing sodium, calcium, silicon, and oxygen could not be elucidated by X-ray diffraction. So there was nothing that people could get from X-ray diffraction because they couldn't grow proper crystals. However, using electron diffraction, so they could identify which of the polymorphs they had. And I'll use this slide here to say that electron diffraction is really useful with inorganic and intermetallic compounds that can crystallize in several different phases with different stoichiometry and often as nanoparticles. And that's when electron diffraction, or this is one domain when electron diffraction can show its full force. Interestingly, the authors of that paper have also written the following quote, basically in their publication, and I will read with you if you don't mind. So 3D ED, which is another way of calling MicroED, has transformed from an exotic technique for crystal structure determination into an indispensable method for problems where small sizes of the crystallites is an issue. And that totally echoes what I explained a few minutes ago about how electron diffraction is able to analyze submicron particles. So we have also solved the crystal structure of many MOF samples, activated or not, using electron diffraction. Here are a few examples of electron diffraction collaboration we've had with Professor Omar Farah's group at Northwestern University. So we've been co-authors in this paper, in this JAX paper on the left-hand side here on a MOF sample used for carbon dioxide capture. Here is another JAX paper we got with Professor Farah on another MOF sample used for sulfur dioxide uptake. And the third paper here in Angewandte Chemie this time on a MOF compound or MOF material that was used for the separation of propane versus propene. So anyway, so Robert will tell us more such stories. The following presentation will be given to us by Dr. Jessica Birch. So Jessica is a brilliant young scientist who's worked for many years with Professor Jose Nelson at UCLA and Caltech, and who has joined us at Rigaku less than a year ago. So Jessica will describe to us the entire workflow of an electron diffraction experiment, from preparing a grid to solving the crystal structure. And she will explain that workflow both at room temperature and in cryo conditions. Indeed, cryo conditions must be used when crystals contain water or other solvent molecules in them. And you do that by using a specific type of grid holder that is also equipped with a dewar. So by pouring liquid nitrogen in that dewar and via conduction, the grid that is deposited at the very tip of the holder here is also cooled down to liquid nitrogen temperature. Okay, and really, if you want to be serious about running electron diffraction, you must be able to routinely run this analysis in cryo conditions. And then Jessica will also talk about another very important topic: how easy it is to use electron diffraction, maybe in your own lab. So indeed, you must be wondering how hard it is to use an electron diffractometer and whether you need any background in electron microscopy itself. The answer is no. And this is when the concept of a dedicated electron diffractometer comes into play, whereby the hardware and software are tuned and designed specifically for diffraction and for crystallographers to use, not for electron microscopists. Okay? And so Jessica will tell us more about that. So the next three presentations, for those we will switch gear a little because they will be dedicated each to a specific field: pharmaceuticals, battery materials, and MOF research. So the first one of these last three presentations will be given to us by Simon Bates. Simon is the business development manager at Rigaku US, and he spent prior to that several years working in the pharmaceutical industry. So he will tell us about how to use electron diffraction, or how electron diffraction is becoming a game changer in drug research. So he will first tell us, excuse me, how to get connectivity and crystal form, even if you don't have enough material for usual analytical methods. You know, these first solids that you get when you first attempt to solve to synthesize a new compound, and you have so little that you can't run much analysis on them. Well, remember that if you have a few particles that you can still see with your eyes, then you should have enough to run electron diffraction. It will also show us how to get connectivity and crystal form, even if the crystals are tiny and imperfect, and even if solvent molecules are imprisoned in the lattice of the crystal, and therefore the crystals must be protected. This is the cryoprotection I discussed a minute ago. He will also tell us how to map out a polymorph population and characterize each polymorph. And that's why a few minutes ago I mentioned to you the concept of high throughput screening of a powder sample using electron diffraction, again, because you have a lot of tiny grains available at once for analysis on a grid or on a TM grid. And lastly, Simon will also tell us how MicroED can help study disorder in crystals when they are milled and processed to make them smaller. The last episode will be led by Professor Joshua Bocarsley. So Joshua is a young professor at the University of Houston, Texas, working on battery materials. And since battery materials are oftentimes poorly crystalline and in the form of nanocrystals, Joshua has been led to investigate the opportunities electron diffraction can provide on such difficult materials. So he will tell us how to assess the solid-state arrangement of atoms in battery electrode materials. And he will also tell us how electron diffraction can help with the study of ordering between sites occupied by sodium atoms and sites left vacant. Indeed, so during charge and discharge of batteries, so sodium ion cathodes undergo crystal structure changes because precisely the sodium ions are being added and removed from the battery material. And the way the crystal structures change directly influence the efficiency of the battery and its long-term stability. So the question is therefore as to whether one can locate the sodium ions in some of these crystal structures, or even more, whether the ordering between vacant sites and sites occupied by sodium can be assessed. So on our own, we've done some preliminary studies at Rigaku on battery materials made of a mixture of nickel, cobalt, and manganese. And these are the blue spheres shown on that picture. The red spheres here are oxygen atoms. And it turns out that once we can solve the structure of the main framework made of the metal sites and the oxygen sites here, the electron coulombic potential map shows basically maxima for the lithium atoms, and these are those little blobs that you see between the oxygen atoms. And so those suggest that the lithium positions can appear well defined. So this material was we use lithium atoms, not sodium. Okay? And so it turns out that once we place the lithium atoms at these maxima, so the full model could be successfully refined using a program called IANA 2020. But again, Joshua will tell us more about that. And the very last episode of our series will be led by Professor Russ Forgan from the University of Glasgow. So Russ will show us how he's applying electron diffraction to his research on metal organic framework. Okay? So he'll tell us how to obtain connectivity even from nanocrystals, because again, MOF compounds are one of those fields where it is usually hard, maybe even impossible to grow crystals. If you have a powder and the powder is crystalline, then electron diffraction may save the day. And that's what happened here in this project. This is a paper that Ross's group published last year, and they showed that by a careful modulation of the self-assembly of the clusters, here the zirconium-6 cluster, with the linkers, along with careful control of the exfoliation conditions. This allowed Ross's group to isolate the first 2D nanosheet built from a zirconium-6 cluster. Okay? So this is not a 3D MOF, this is a 2D MOF. And the problem here was that they could not characterize the different MOF compounds that they were synthesizing in the course of their synthesis attempts, because they could not grow they could not grow crystal for X-ray crystallography. And again, electron diffraction saved this project. Here is a picture of crystallites or small particles they used, and an example of a diffraction pattern they got from this. And so Ross after that, Ross will also tell us how electron diffraction is better to study solvated and empty MOF lattices. Here, the thinking is really simple, is that the very fact that crystals for electron diffraction are so small also makes it easier to fully load them with guest molecules, because the diffusion pathways to the core of those small crystals are smaller, and also one can work with less guest molecule. So therefore, using tiny crystals are better with electron diffraction, are better to study solvated and empty MOF lattices. And lastly, very lastly, Ross will also show us how electron diffraction is the only method that can catch transient MOF species between conformations, be they between closed and open conformations, or between solvated and empty conformations. Okay, and I will stop here. I hope I have explained clearly what crystal structures are and the kind of information you can get from them. And I hope that I have also shown you how electron diffraction is becoming really a game changer in many, many different research fields now. And I'm happy to take a few more questions if we have time for it.
Well, of course, thank you very much, Pierre. That was very nicely delivered. So we do have quite a few questions, and we'll see how we get on. I'll just take them in order. So are there any challenges confirming hydrates and solvates due to temperature vacuum during measurements?
Yeah, so that's exactly the point. So electron beams are under high vacuum. And when you load a grid of crystals of a powder without protecting them, if you have water molecules or solvent molecules in those grains, they will evaporate from the crystal under the strain of the vacuum. So that's why you absolutely must protect those crystals first and pre-freeze them at liquid nitrogen temperature before to even load them into the diffractometer, and therefore before loading them into the vacuum of the electron beam.
Okay, thank you. Can compounds present in solution be missed by crystal structure analysis?
Sure, they can. So again, it's all depends as to whether your compounds can crystallize in the solvent that you are using at that moment. If this is a compound that is highly soluble, then it will happily remain in solution and not yield crystals. And in those cases, well, if your compound does not crystallize at all and remains in solution, obviously you can't get a crystal structure for it. So you need to have at least a precipitate, some kind of a solid coming out of solution. And then if that solid can crystallize in large enough crystals, you use X-ray crystallography. If that solid remains as tiny grains of powder, you use electron diffraction.
Okay, thank you. Thank you. Oh, I can hear myself on your side.
Oh, really?
Yeah. Okay, so the next question. My interest is in structure determination of small molecules, which you've already talked about. I think this question came in before the break at slide 20 or wherever it was. So my colleagues often work on problems related more closely to materials science or engineering. Has ED been used much yet for ceramics, cements, materials under stress, or other similar applications?
So not too much as far as I know, but these are exactly fields of research that we would like to start investigating more, besides just using electron diffraction to get a crystal structure. So I can't tell you much about it yet, right? But this is definitely fields that we would like to investigate further with electron diffraction. And certainly, if you want to get in touch with us and send us samples, start a collaboration, we'd be happy about it. But I can't say more than that at the moment, unfortunately. Electron diffraction is still pretty new, especially in the home lab. And then we haven't gotten to all these different applications yet, which I'm sure more and more applications will come up to people's minds in the future.
Yeah, I believe that the University of Warwick, which is one of our customers, is studying ceramics on their system. Okay, so how do you choose the type of grid depending on what factors?
Oh, no, I mean, we use, in our lab here, we must use 3 or 4 different types of grids. We don't have a specific preference usually. So I can give you, I'll make a few comments. So the lacy type of grid have a less flat, less even surface. And that causes the crystals to add up slightly different orientations on the grid. And therefore, when you collect data on 2 or more different crystals, because they each have a slightly different orientation in the beam, instead of being just flat on the grid, so you may be able to collect more complete data sets. Okay. So that's an advantage of lacy type of grid versus this flat, completely flat carbon or surface made of carbon polymers. The quantifoil grid, we like to use them whenever we use samples that decay quickly as soon as they are taken out of their crystallization solution, proteins, but also other small molecule compounds, right? So the thing is that you can't, you have to leave those crystals as long as possible surrounded with their crystallization solution, but electron diffraction should be done on samples that are as dry as possible. So you've got a bit of a dilemma there, right? So the way to handle these kind of samples is that you deposit a drop of a slurry on the grid, and then from the opposite side of the grid, you blot the extra liquid for just a few seconds, and then flash freeze whatever you have left on your grid into liquid nitrogen. Now, to blot the extra liquid, it is actually easier to do so using the quantifoil grids, because those quantifoil grids have definite holes in them. And then, so from the opposite side of the grid, opposite from where the powder is, or the compound is, so it's you can basically take out this extra liquid faster and easier. But these otherwise, besides these 2 tips that I can give you right now, I can't think of anything that makes us prefer one type of grid rather than another.
Okay, we're running short on time, so maybe one more question. Does the grid itself, the carbon grid, influence the diffraction pattern?
No, Absolutely not. The diffraction pattern does not. The grid does not influence the diffraction pattern, and will yield a overall background on your diffraction images, but nothing more than that. So the discrete reflections from the crystals will clearly stick out of that tiny background created by the grid, or even whatever liquid you have left on your on the grid along with the crystals. So you don't have to worry about worsening your data using one type of grid versus the other.
Okay, so I think we'll call time there. There are still 11 open questions. We will respond to those offline. So thank you very much for your interest. Before we go, I just wanted to also share that, as Pierre has explained, there are more lectures in this series. And if you have not registered for all of them, then please do so. I don't know if you have that webpage still open, Pierre. If not, I can share it just at the end, just to show everyone.
Yeah. Let me stop sharing my screen here.
So we just want to make sure that you don't think you've registered for all of the lectures when maybe you accidentally only registered for the first. And yeah, please do check and register for all of them if you find the content interesting. So while Pierre's doing that, I'd just also like to remind you again, we have recorded this webinar, and the recording will go online tomorrow. And I think you should get an email to remind you of this.
And so then the next presentation, as I explained in my own presentation, is going to be given to us by Robert. He's going to tell us about how electron diffractometers work and about real-life samples that we analyzed in one of our Rigaku labs.
Yeah, so maybe I should also point out that the daylight saving time is currently in effect in America, but not yet in Europe. So the time for this seminar next time in Europe will be 1 hour later, but it will be the same time in the United States. Okay. Anything else, Pierre? Or I think we're finished.
I think we're done. Thank you very much, everybody. Yep.
Yeah. Thank you, everyone, and we'll see you next time. Goodbye.